So for a process, okay, for a reaction, for a change, what we are most interested in is not actually what is the entropy of the initial and what is the entropy of the final. What we're interested in is the change. Okay, that's because entropy is a state function, just like enthalpy was a state function. If something is a state function, that means you can just look at final and initial, and you can take the difference, because it doesn't matter what way you got to the final state, it just matters what it is at the final state. Okay, so we will be calculating not just S, but we will be looking at and calculating and talking about delta S. So if I say entropy, I mean we're talking about delta S, because that's what we talk about. Okay, so delta S, right, of any kind of reaction would be the final value minus the initial value. Yes. Okay. Like I said, we're not actually going to really just be subtracting numbers. We're going to do other ways to calculate delta S. One of the things that we can do is we can predict the sign of delta S. So this is not predicting spontaneity, okay, because entropy is just a part of what spontaneity is. Entropies can be positive or negative. Okay. Right now, I'm not going to tell you what it means if it's positive or negative just yet. We got to get a little further. But just like delta H, you can have positive or negative values. So how are we going to predict the sign? When we look at a reaction or a process, okay, one of the first ways you can predict is you can look at the phases or the phase change that's happening. Okay. Generally, what do you think is more, and I'm going to use the word disordered, or maybe I should say, what is more free? Solid, liquid, or gas? Gas. Gas is a substance in the gas phase has more entropy than a substance in the solid phase. A substance in the gas phase, gases have more entropy than liquids, which have more entropy than solids. Yes, absolutely. A phase change where you go from solid to liquid, so that melting, right? Melting. That would be increasing delta S or decreasing delta S? What do we think? Positive value or negative value? If I'm going from solid to liquid, positive. I'm increasing the amount of entropy, right? If I go from gas to liquid, if I condense, my delta S for that process would be negative because it's decreasing. Yes. Okay, so we can look at the phases. We can look at temperatures. Typically, low temperatures means lower entropy. Right? Higher temperatures means higher entropy. Why? Well, entropy is about how spread out matter and energy can be. At higher temperatures, you have more thermal kinetic energy, don't you? More energy, more ways to spread out, higher entropy. Okay? You can look at the mass of these substances. You can look at the type of particle that you have. You can look at that. Right? We're just trying to make predictions, yeah? If you have particles that are very small, don't have a lot of mass, what do you think about the amount of entropy? Small. Lower entropy. Small particles, lower entropy. Bigger, heavier particles, bigger entropy. More ways to spread all that jelly out, right? Larger particles, larger entropy. And then the fourth thing, okay, that you can look at and think about is the types of particles you have mixed together. Okay. You have a mixture of different types of particles. What do I mean when I say a different type of particle? Really what I mean is different phases. Okay. You have a mixture of things in several different phases. Okay. You got a lot of different combinations and spreading that can happen. Those tend to have higher entropy values. They get more, there's even more ways to spread out, higher S values, yeah? So look at on your in class, look at number, I guess it's 3. And so I edited this for this semester. You guys should have 4 questions, right? On part 3? Okay, excellent. All right. I cut it down some. Let's try to make a prediction. So again, what am I doing? I'm comparing final and initial sides. In a chemical reaction, what's the final side? Product side. What's the initial side? Reactant side. And I'm trying to predict, will delta S for what I'm looking at be positive or negative? That's what we're trying to do, yeah? So that first description of a process, 1 mole of liquid water at room temperature, and I changed the temperature of the water to 50 degrees. I didn't do a phase change or anything yet. I just increased the temperature of the water. What would you predict the delta S of that process to be? A positive value or a negative value? Absolutely. This process is increasing the amount of entropy. Delta S would be a positive value. Because why? We increase the temperature. Okay, what about this process? Silver and chloride ions, when they come together, they precipitate, right? They solidify, right? Okay. On the reactant side, I have 2 particles in aqueous solution. So that's water and particles all running around together. And then on my product side, I got a solid. Is my entropy decreasing or is it increasing here? It is definitely decreasing. Why? Solids have very, very, very low entropy. I took it from lots of entropy to very little entropy. Negative. Okay, C is an interesting one. There's a lot going on in C. Here's what I would look at in a situation like this. Okay, what phase of matter has the most entropy? Gas. How many gas particles do I have on this side? 7.5, right? 15 halves. 7.5, yeah? How many do I have on this side? So I have more moles of gas initially, and I have less moles of gas finally. What do you suspect delta S is for this? It's negative. Because why? In my reaction, I ended up with less gas. And the less gas you have, the less entropy you have. What about that last one? I'm going from CO2 in the solid phase to CO2 in the gas phase. What's that called? What's this phase change called? Very good, Joseph. Sublimation. This phase change goes from solid to gas directly. Guys, that's a huge increase in entropy. Delta S is positive, for sure. Okay. And that's the end of section 2. I told you guys y'all were going to like this chapter. I told y'all. Didn't I tell y'all? Okay. Let's go to section 3. There's 2 chapters on the next test. The one after tomorrow's test, yeah. 17. It's going to be 16 and 17. 17 is electrochemistry. It's redox reactions. Ooh. It's galvanic cells and batteries and electrolytic cells and fuel cells and all kinds of fun stuff. Oxidation reduction. Okay, but we're here to talk about the laws of thermo. So in section 3, we're going to talk about the first, no, not the first, the second and the third. And I think we can talk about the second today, and then we'll have to save the third for, ooh, so not tomorrow. Well, later. Okay, so what is this? Does anybody, most people, if you say, what's the first law of thermodynamics, most people can cobble together some kind of something about you can't create or destroy stuff, right? Most people can kind of have that. Does anybody in here know the second law of thermodynamics? I didn't think so. Nobody ever knows this one. Poor little second law. Nobody ever knows this one. Yes, it's the redheaded stepchild. I can say that because I'm redhead. That's why I can say that. Okay, I can say that. Let's try to let's just say the second law in words. Here's the second law. The entropy of the universe is always, and not just changing, increasing. Very specifically, the entropy of the universe is always increasing. Yeah. On what? Oh yeah, I think that was a miss. Yeah, I remember that. Yeah, I remember that. Correct. The entropy of the universe. What do I mean when I say the universe, you guys? What do I really mean? I mean the whole damn universe. I mean the universe. Everything. Everything. The universe. Everything. We're going to write this in math. I'm talking about the entropy of the universe is always a positive value because it's always increasing. All processes that are spontaneous and are where? In my lab, right? Just in my lab. In the whole ass universe. All spontaneous processes that happen cause the universe to increase. Any process that's spontaneous is just causing the entropy of the universe to get bigger and bigger. If you guys ever heard that phrase, the universe is constantly expanding. So actually what that is referring to is this law. When people say, oh, the universe is constantly expanding. Yeah, the entropy is expanding. The entropy. And what is entropy? How spread out matter and energy get. The universe is constantly expanding. Okay. How can I calculate delta S of the universe? Well, how do you calculate any delta if you have a reaction? You final minus initial, right? Okay. I don't have a reaction here. I have a billion, gajillion, quadrillion, sextillion reactions, right? Okay. So what I'm actually looking at when I talk about delta S of the universe is kind of more of a throwback to any thermo process. In thermodynamics, we only look at two things. What are the two things? System and surroundings. The change of the universe is simply the sum of the change of our system and the change of the surroundings. So in chemistry, our system is usually a what? A chemical reaction. So I might write system or I might write reaction. It's the same thing for us. For us, it's the same thing. Okay. So yet another way I can predict, not yet another way, really this is the way. Here we go right now. How can I use delta S to predict spontaneity? I can't look at just delta S of the reaction alone. That does not predict spontaneity. What predicts spontaneity is if delta S of the universe is what? Bigger, increasing. If delta S of the universe is bigger than 0, then your reaction is, without a doubt, spontaneous. That's the true fact of the second law. Guys, that's the second law. Okay. What if delta S of the universe is a negative number? Then the reaction is non-spawn, right? You're trying to roll that ball uphill. It's not spontaneous. Okay. I don't know how much. Oh, no, actually, well, never mind. I shouldn't say that. Okay. S universe. What if you have the change in the universe is 0? That means your reaction is in equilibrium. Okay. Your reaction is an equilibrium reaction. It's not increasing nor decreasing the universe. It's holding steady. Okay. Ooh, that has a lot of information on it. Okay, y'all just look at me. Y'all look at me. Y'all look at me on the board, not the slide. It has a lot on there. Okay. So I want to know, how can I calculate delta S of my reaction? If I had values, I could do final minus initial, right? But to get those values, you got to count how many microstates you have. Yeah, we don't want to do that. I mean, I don't want y'all to have to do it. Okay. If I knew the universe value, I could do some math here. Okay. Also, don't really want to do that. So here's a first way to actually calculate delta S of a reaction. Okay, calculate. Not just predict the sign, but let's calculate. We can calculate it using, what is Q again? The heat of the reaction. We can calculate using the heat of a reaction. In this chapter, the Q equation that we're going to use the most is actually the moles times delta H version. Could you use MCAT? Yeah, but I'm telling you guys that we're not going to have those specific heat capacity problems here. Okay. So we can calculate delta S using Q. Here's the equation. The delta S of your reaction should always be bigger than the heat of your reaction divided by the temperature. What temperature units do you know that we have to use here in this chapter? Yeah, Kelvin. Okay. We're going to have to use Kelvin here. Okay. When you calculate Q, what units are enthalpy usually given in? Usually these are kilojoules per mole, right? These are kilojoules. What units, so our Q value is going to end up in kilojoules, right? But what unit did I tell you S is reported in? Joules. I know. So you're going to calculate this, and you're going to have kilojoules per Kelvin, and you're going to need to change it to joules per Kelvin. Y'all remember how to do that? I don't know. There's 1,000 joules in 1 kilojoule. Okay, there you go. So if you're looking at this and you're like, but Miss Poe, that's not an equality, that's a inequality? That's not an equal sign. All I can do with this is tell you that the value would have to be bigger than X, right? That's all I can do with this. Okay, sometimes that's fine. But I'm telling you that if your reaction is at an equilibrium, what kind of reactions are at equilibriums that I'm telling you right now is the ones you're going to be seeing here in this class? Actually, phase changes. Phase changes are an equilibrium. Y'all remember that from chapter, first chapter, chapter 10? Right, on our little heating curve, what do you have right here? You have solid in equilibrium with liquid, right? And then you have liquid in equilibrium with gas. Okay, those are equilibriums, right? If your reaction is at an equilibrium, then delta S does indeed equal the reaction divided by the temperature. Then it's an equality. So let's try 2 and then be done. 2 or 1? 2. I don't know. Look at number 4 and number 5. Yeah, let's do those two. Pretty straightforward, pretty easy. Write the phase change. Oh, why is that? Oh, well, that's fine. What is the phase change that's described in question number 4? What's the word that's the phase change word in this problem? Condensing. Guys, do you, before we do the math, do you predict condensing the sign of the delta S that we're fixing to calculate? Do you predict for condensing the sign is going to be a negative or a positive value? Let's predict something first. Condensing means going from what to what? Gas to liquid. You're getting less entropy. I predict it's going to be a negative number. Let's see. What do I use to solve for delta S of a reaction when it's at equilibrium like a phase change, like what we see here? I need Q of the reaction and I need the temperature of the reaction. That's the two numbers I have to divide. When you read this problem, what did I give you that you can use to solve for Q? Okay, you have moles of this compound CCl2F2. And I gave you, okay, I gave you delta H of vaporization. And I gave you a temperature of 25 degrees C. Okay. So Q for a reaction equals moles times the delta H for that reaction. How many moles do I have? I have 1.20 moles. What if I gave you grams of a compound? You convert it to moles using molar mass. More math. Okay, what's my delta H? There's that laugh. Guys, this is the enthalpy of vaporization. Are we vaporizing here or are we condensing? We're condensing. Recall, the delta H of vaporization is the negative delta H of condensation. Recall that from chapter 10 in this class. This is not Gen Chem 1. We learned this year. 6 weeks ago? I think it was like a lifetime ago. I don't even know. It was so long ago. So you have to remember, if I told you vaporization, but we're talking about condensation, guys, a big fat negative sign right in front of that. With the negative sign, now that's condensation. Okay. Negative 20.6. What units? Kilojoules, because look what happened to my moles. My moles canceled. Okay. So when I go down here for the actual problem, which is solve for delta S, I have to have my Q of the reaction in joules. Yeah, I got to have my reaction in joules, not kilojoules, for this calculation. And then I'm going to need my temperature. So I'm going to convert my answer in kilojoules. And you can show this step if you want to, or you guys, I'm really going to have to just trust at this point that you guys understand that you're multiplying this number by 1,000. Okay, and you can just give me the number. Okay. So 2.06, sorry, negative 2.06 times 10 to the 5th? Fourth. And there's no moles, it's joules. There's no moles canceled. Right? Moles are gone. Moles canceled. Moles are gone. Now we're going to divide by the temperature in Kelvin. So negative 2.06 times 10 to the negative positive 4. Sorry. So I'm so used to negative exponents from the last 2 chapters, 5 chapters, whatever chapters that we've done. Joules divided by, so I had 25.0 degrees C. So that means my temperature in Kelvin is 298.2 technically, but I just keep the whole 1.15. I don't know why, I just do. Negative 69.2. What are the units here? Joules per Kelvin. There you go. Very good. You like it? Is that simple enough? Good. Good. Okay, we don't have to do number 5 today. I mean, y'all can do it if you want to, but it's the same. It's the exact same thing we just did. There's the answer. If y'all want to jot the answer down, you should get an answer of 120, positive 125 on number 5. You should get positive 125 joules per K. And we got a negative number like we predicted, didn't we? Okay. Well, I would say I would open up this first set of homework tonight, but I'm not going to. Yeah, I'm not going to. I do think, though, do I only have one homework set? No, I have 2 sets, but I think the first set is pretty, I don't want to use the word rinky dink, but I'm gonna. Okay. It's pretty not hard. It has 17, right, as of right now, it has 17 questions on it. This first set per chapter, it has 17 questions with a suggested time of 21 minutes. Okay, so not the homework for this first part of section, chapter 16. But I won't open it today. I'll wait. Because, I'll wait and I'll open it tomorrow. Because you guys need to focus on test tomorrow. So, probably not Monday, probably Friday. 17 questions, 21 minutes. You can do it tomorrow after the test.
No, I got to study for math.
Oh, yeah, that's right. Y'all got a math test. That sucks. You can do it Thursday after your math test.
Thursday, I'm going home, flopping onto the bed and knocking out.
Sounds like a personal choice you're making about your education right there, Loretta. Sounds like a personal choice to me. Okay, let's go down to the lab. Clean up. And y'all ask me whatever you want to about acid base. I can work problems. I would like to work together one more equivalence point problem. Yes. And I think I'm going to do that one from our unit. Whatever, from the in-class examples. I already have that one typed. I guess we'll do that one. But I'll answer whatever I can, okay? And grab your note cards, yes? Grab your